Okay, good. So our next speaker is Nicola Franco. He is also doing PhD at Politecnico, and he will talk us about learning the solution manifold of parameter-dependent PDEs using deep neural network. So Nicola, I leave you the stage.
Thank you very much, Lorenzo, for the kind presentation. And so let me share my work with you. I'm very glad that I have this opportunity to participate to these seminars. So the topic is that of parameter-dependent PDEs, and the idea of using deep neural networks as a tool to, in practice, make feasible the learning of the solution manifold. And let me clarify what I mean by that. So the framework is that of, you have some kind of phenomenon that you can describe using PDEs, for example, the movement of water. And this PDEs, your model typically involves many parameters. It can be finitely many, infinite dimensional, but I will focus on the finite dimensional case. And based on the values of the parameters, you obtain different solutions, and you can describe different evolutions or, in general, phenomena. Another possible case is that of disease. When you look how disease can spread within a population, and you have the rate of spreading and many other parameters that can enter in your equation. For example, in this case, the shallow water equations, you have the density of the water, which, for example, if you assume that to be some sort of, well, maybe not a constant, but possibly you have two different densities subdivided in different regions of the space, it becomes a problem with two parameters, and we will see many others. But the point is that when you have this type of situation, a model depending on a PDE and on multiple parameters, you can encounter different problems. The first one is, okay, I have this model to describe this phenomenon. Now I want to know which are the values of the parameters I should put inside to obtain the correct predictions about reality. Okay, so possibly you start from looking at the phenomenon in the real framework, you do some measurements, and you want to say, okay, so in the model, which are the values of the parameters that match, that correspond to this real data that I have measured. This is a problem of inverse uncertainty quantification. And the other possibility is, maybe my problem depends on these parameters, but I'm not pretty sure on the values of the single parameters, so they can be uncertain. And the question is, if the parameters are uncertain, then the solution becomes uncertain and the predictions too. But how uncertain they are, where do they oscillate possibly? And this is the problem of forward uncertainty quantification. Last but not least, another framework of interest is that of optimization, where, for example, you may have, say, for example, the case of heat in a room, and you want to understand where is the correct location of windows along the wall to maximize some type of movement of the air that you may want in your room or not. So changing the values of the parameters in order to obtain the solution that maximizes some type of functional that you are interested in. The point is that all this type of stuff requires solving the PDE many, many times. For example, consider the case of estimating the parameters in the model. Well, one type of approach that you have is that of statistics in the frequent framework, which is estimates based on the maximum likelihood estimates. So for example, you have some measurements, you take a guess on the possible parameters in the model, and you see, does this guess match the actual data? If it doesn't, let me change the value of my parameters so that it moves accordingly to the actual measurements. So you try to adjust the parameters, but every time you change the parameters, you have to solve the PDE once again, because you have a different model. You have to solve it in order to see if the model matches the real data. So you have to solve the PDE many times, and doing this can be very, very expensive. even though we have, in the literature is plenty of very good methods such as finite elements and many others. They're very efficient, but if you have to apply them many times, maybe on a very fine grid, this is going to be very expensive. So we want to boost things up by substantially learning the map that to each parameter makes turns out the corresponding solution. Okay, as we change the values of the parameters, this corresponding solution changes, and what we want to understand is the whole set of possible solutions, what we call the solution manifold. So if you wish, the whole framework, in the case of, for example, a stationary model where you don't have time, you may describe it as follows. You have the abstract model, and for each parameter, value of the parameter mu, which may vary inside a parameter space theta, which you can see is finite dimensional. So I'm supposing I have p parameters. To each parameter, I associate the corresponding solution. And the solution, I will use the approach of seeing the solution as an element of L2, which if you have some background on PDEs, etc., possibly variational formulations, you may be used to see solutions inside other spaces, sublet spaces, etc. But I will use L2 for different reasons. The first one is that it's simpler, but it's also because I will consider cases where we have singular terms in the PDE, so you won't be able to find a solution in a sublet space. So to that abstract model, you have the corresponding full order model, which is what you would get by employing, for example, finite elements. For each parameter, I have the corresponding solution, which is very high dimensional because it's my approximation using finite elements on a very fine mesh. So to each vector mu, I'm going to associate some high dimensional vector uh mu, which lives in the space R and H, where NH are the number of vertices in the mesh, so it can be very large. Now, what I want to do is understand how this mapping works and try to approximate it using some other tool and not having to implement actually the finite element method every time. How to do that? Well, there are many possibilities, but all of them follow a common skeleton, I would say, which is the driving idea of reduced order models, which are usually termed ROM. The construction of a ROM, which, as I mentioned, is to boost the capacity of the full order model and make the computations less expensive. The idea usually is the following. You employ the form, for example, finite elements, which you trust very much because you believe that the solutions that you compute using that method are very precise. And you compute the solutions for some number of parameters. For example, say that theta is your parameter space, and you sample 1,000 random possible values of the parameters, and you compute the corresponding solutions. Now, the point is, these are some data. Now, train some other model and fit the ROM in such a way that it understands why a certain mu is associated to some solution, and it tries to generalize on the other instances of the parameter space. This is not different from trying to do fitting of a regression model of interpolation. Okay, you have some values at some given abscissa, and you try to approximate the function in the whole interval. In a way, it's the same idea. Okay, so that's why we are going to see this as a problem of statistical learning. Because starting from the data, you try to understand how things work out. And these two steps can be seen as an offline stage and an online stage. The offline stage is the one that is pretty expensive because you have to solve the PDE many times using the big solver. So for example, finite elements. And it's also the one that takes longer, but you have to do it only once. You only have to collect the data once. After that, once you have collected the data and fitted the ROM, you have your reduced order model, and you can run it as fast as you wish. And then you have the online stage. Okay, so the ROM is ready, you can use it, and for example, you can employ it for solving the tasks that I mentioned at the beginning, such as the estimation of parameters or optimization tasks. But how do we actually build the reduced order model? There are many possibilities, and I will start by presenting the most classical one, which has been then investigated in several possible variants, but the grounding idea is practically the same. So what you say is that, well, let me assume that I have a representation of this type. So each solution, U of mu, can be seen approximatively as some linear combination of some, you could think of these as fundamental solutions, or in any case, some type of basis, which are this psi k, psi prime k, and the values of the parameters simply correspond to enter the solution, in fact, through the coefficients, okay? So when you change the parameters, you are changing the coefficients on the expansion that you have on this basis. This is a very easy idea, but it's also one that works particularly well in some problems. And it's the founding idea of reduced basis methods. What you have to do, starting from the data that I mentioned, is understand how this basis is done. So try to see which basis is able to span through all the data that you have. And then you have to learn the map that to each parameter associates the corresponding coefficient on the expansion. The finding of the basis is pretty standard because we have some optimality results that are based on classical projection theorems. So the psi prime k is not a big deal, it can be computed. Instead, the approximation of the correspondence from the parameters to the coefficients can be much more complicated, and there are many possibilities. For example, polynomial chaos expansion assumes that these coefficients depend polynomially on mu, so you can do some type of fitting using these further properties. Then you can have instead the POD Galerti methods, which have been very popular and work very well on elliptic problems with affine coefficients. In this case, the idea is, well, assume that the solutions admit an expansion of this type. Then I'm going to write the weak formulation of the PDE by exploiting the fact that the solutions live inside the space spanned by the C prime K. So in fact, I can project the whole PDE in a low dimensional space. Here you see that the basis consists of n functions. So it would be a projection of the PDE on n dimensional space. And you solve the PDE on this reduced space, which is much easier with respect to employing classical finite element. This is possibly the most intrusive approach because every time you want to compute a new solution, you still have to solve the low dimensional version of the PDE. So you still have to do some computation. Instead, polynomial chaos expansion, once you have fitted the polynomials, well, you can compute new solutions in seconds, in fact. And other alternatives concern, for example, deep O-nets, which have been investigated a lot by Lulu and Karniadakis recently, also Siddhartha Mishra, and many others. But the idea is to use neural networks, but it's still bounded to this type of expansion of the solution. So you still have something that works in this way. And the problem is that all these approaches, as they assume an expansion of this type, will have some limitations. Which are the limitations? Well, in fact, by using this type of expansion, you are assuming that the parameters only influence the coefficients, So after you have fixed the dimension n of your reduced basis, you are assuming that the whole collection of solutions lives in the span of these functions. So lives inside this n-dimensional space. Geometrically speaking, this means that your whole solution manifold, which is a subset of L2, is being approximated by a linear space, subspace, if you wish, of dimension n, where n you have to fix it at the beginning of the construction of your ROM, because it defines the reduced dimension where you wish to work. And of course, approximating some type of manifold in general using simply some plane can be a bad idea in some cases, especially if the dependence on the parameters with respect to the solution is highly nonlinear. And in that case, the approximation may be good near some points, but very bad outside of from that. And that fact depends, of course, on how wide the parameter space is, but also on the many other properties of the PDE. And the two important properties are space localized effects and convection fields. In general, if you have a source of transport in your equation, your manifold is going to be the more nonlinear. Okay, so it increases the nonlinearity of the manifold. And this should make sense, because if you think, for example, at the transport equation in 1D, you may even forget about the parameters. Classical example in any course in PDEs, you have your little mountain that moves as time goes on, and the solution is simply a traveling wave. And what's the point? The point is that if you think about this wave that moves, well, take some time steps, maybe with some intervals of waiting in between, and all these mountains are going to be very separated from each other and are going to be orthogonal in L2. As they are orthogonal in L2, it means that you need more and more dimensions to approximate the whole set of solutions. If your solutions are traveling, every time they travel, it's like they turn 90 degrees in the infinite dimensional space of L2. So you have this type of curve that keeps turning 90 degrees infinitely many times. And it's going to be very, very difficult to approximate it using a linear space. And how bad is the approximation, or how good, can be computed in many ways. And a standard reference is that of the so-called linear width, or Kolmogorov width, as Kolmogorov first introduced the concept back in the days. And it's computed as follows. Here you see the version where substantially I'm forgetting about the fact that the solutions are in L2, and I'm just saying, okay, let me use the form solution, so the high fidelity version, the one with many, many degrees of freedom, as a substitute. But you can write this formula in the same way also in L2, just simply substitute this matrices V with some projector. But the point is, as you see, that you are saying, well, look at this W, which is one possible solution. I'm going to approximate W with its projection on the space spanned by the columns of V. Okay, so you are doing precisely the choice of a linear space and seeing how good you can be. In fact, see that I'm taking the suprema with respect to all possible solutions. So it's the worst case error that I can make among all solutions, and then taking the infimum among all possible subspaces of dimension n. So I'm trying to fix the dimension n, which is the best linear subspace that approximates the manifold, and compute the error. This is the Kolmogorov width. And of course, as you increase n, you have more dimensions, your space is going to be larger, and your approximations are going to be better. But as I mentioned, there are cases in which you can keep adding dimensions, but this worst case error, this Kolmogorov width, is going to decrease very slowly. So if you want to have a ROM that is sufficiently accurate, you need a very large n. But if n is very large, it's going to be a problem, because your computations are going to be expensive. Okay, if n is large, even the reduced order model is expensive and it doesn't make sense anymore. So what I'm going to do is try to exploit other objects and methods that are nonlinear and try to see if we can overcome the limitations of these approaches. And the idea, brutally speaking, is to employ a neural network, which is a nonlinear approximator that directly maps the parameters to the high fidelity solutions. Given a parameter mu in RP, I can directly give you the whole solution on the high fidelity mesh. And as you may expect, this is going to be a very, very massive network. But how to construct it? That is the first problem. And before going on, let me give a very quick recap on what are neural networks, even though I believe that many of you already know this because they've been very popular in many, many areas. But in general, a neural network is simply some type of map that depends on some parameters that you can tune and optimize them in such a way that your network is as good as possible. In general, how are the networks obtained? Well, the networks are obtained by composition of layers, where each layer is a function of this type. A layer is, in fact, the composition of an affine transformation and an activation, which is something that is nonlinear. For example, I can take an affine transform of this vector v by multiplying through the weight matrix and summing the bias. This is going to be an affine transformation. Then I apply the activation rho, which is a scalar function that I'm going to apply to each component. For example, rho can be the square. Okay, I'm going to do the affine transformation and then square each component in the vector. This is the idea. You can use different activations. I'm going to use the ReLU function, which is simply the maximum between the scalar value x and 0. So it's going to be 0 on the negative numbers and the identity for positive numbers. This is a possible choice. And the point is, you define the layers, the activations are fixed, you have fixed it, but you don't know the weights and biases. And you are going to optimize the weights and biases in such a way that the network, your map obtained through this composition, is as good as possible, performs well, which in our case means, let's see if on the data that we have collected, the network is able to return the correct solution. I give them the parameters and I see the solution if it's close or not to the actual solutions that I've found in the offline stage. But as I mentioned, there is a problem, which is how do we define this network? And what we are going to do is be inspired by the linear methods that I mentioned. So the Kolmogorov bandwidth, but we consider a nonlinear version of it, which was also called the Manifold bandwidth. This is a typical case in which you start and you believe that you are finding some generalization of something, and then you discover that 40 years ago, someone already did it. This is very common, I believe, and possibly the most common thing between PhD students, but this is the idea. You can see the difference with respect to the previous case. I'm not using a matrix to project on some space. Instead, I'm using continuous maps. Any pair of continuous maps, psi prime and psi, I take a solution, I map it in Rn, which is my latent space, my reduced space, and then I decompress it using psi back to the high fidelity space. What does this have to do with our neural network? The point is that we break the problem of defining a network in two parts. First, a dimensionality reduction, and then the learning of the reduced map. Let me clarify this. The idea is as follows. We don't actually define a single network, but three of them. We have two networks, psi prime and psi, which are going to give us a low dimensional representation of each solution. This works in this way. I give some solution to psi prime compress it in the whole solution into an n-dimensional vector, then I decompress it using psi, and I wish that the decompressed version is very similar to the original one. So I train decomposition psi prime in such a way that is able to reconstruct the solutions as it would be in a linear projection. Okay, I project in a space, and I wish that the reconstruction is very similar to the original one. Once I have the low-dimensional representation of the solutions, well, I still need to connect to understand which is the link between the parameters and the solutions. And this is the place, the work for the network phi. Phi is going to map each parameter to a low-dimensional version of the solution. And finally, the final model is given by composition, because I take a parameter, map it through phi in the low-dimensional representation, and I use the decoder psi to obtain the high-fidelity reconstruction. So this is why we consider this to be a constructive approach. Finally, there is still something to understand, which is the choice of the latent dimension. Because as you see here, I first need to fix the small dimension at the middle of this scheme, which is little n. As in the linear case, I still have to fix the dimension where I wish to work and then proceed with construction. How to define n? Where I'm going to consider the fact that differently from the linear width, the nonlinear one decreases very quickly. In fact, up to some dimension, it becomes identically zero, because there are some dimensions where you can exactly represent your solutions without losing any information. So you are able to compress the whole manifold. How is that possible? Well, it shouldn't be surprising, because the PDE depends on p parameters. So ultimately, your manifold is some p-dimensional manifold. Okay, consider the case of one parameter, you are describing a curve in L2. So it's still a curve. So expect it to represent the curve using very small numbers. Okay, so you expect that you can work in a reduced dimension that is very low. So we define the minimal dimension as the first integer where you can do the perfect reconstruction and go to a zero error. But so we are going to use this minimal dimension so that we are sure that the model can be as accurate as possible. But which is the value of this minimal dimension? This is a theoretical question that can be answered in many ways. Well, first of all, I'm going to give you here the results in an informal way. There are some points that I should clarify: the fact that I'm considering a Hilbert space and ambient space, the fact that I assume the parameter space to be compact. But I'm going to dive very quickly into this, but if you wish, we can discuss about this later. The first thing is that the minimal dimension is a topological invariant for a compact set. So if you have a compact set and you do some deformations using continuous maps, the minimal dimension is not going to change. Second point, with this, the first one is very easy to prove. You just have to be careful because you have to have some control on the errors, and you have to use some extension theorems, but it works out. The second one, instead, it gives you a bound, tells you that in basic conditions, the minimal dimension is going to be at least p, which is not surprising. The p depends on p parameters. I don't think I can represent each solution with less than p parameters, p numbers. The second one, instead, is a bound from above, which is the most interesting one. If you assume the correspondence from the parameters to the solution to be Lipschitz, then you know that the solution manifold has a latent dimension that is at most 2p+1. And this is a bound that you can prove using dimension theory results, particularly the Menger-Nobeling embedding theorem that tells you that if a space has topological dimension p and is separable, then you can embed it in R to the power of 2p+1. And working on that result, you can work things out. Finally, if the map is continuous and injective, the correspondence parameter solution is invertible and continuous. So you can represent each solution with the corresponding parameters. And of course, in this case, the latent dimension is P. I believe I'm running out of time, possibly. I will try to finish it in 5 minutes if that's not a problem.
Could I quickly ask a question?
Yeah.
Yes, so if you go back to the regularity stuff you have there in the previous slide.
Okay.
Sorry, I jumped in somewhere in the middle of the talk, so I wasn't sure of the equations you're looking at, but these issues of the assumptions about the smoothness or regularity of the solution as a function of the parameters, that's the regularity theory of associated PDE. So I guess for the PDE you're looking at, do you a priori know these regularity results?
Well, you can transfer regularity on the PDE to regularity in this sense. Here I'm saying that when you change the values of the parameters continuously, the solution in L2 changes continuously with some Lipschitz control. You can prove, for example, that in the elliptic case, in the case of elliptic PDEs, if the coefficients are Lipschitz with respect to the parameters, then the solution is also Lipschitz with respect to the parameters.
Yeah.
So you have this regularity that
if you have
translates.
hyperbolic, parabolic, or hyperbolic problems, then you have other issues.
Yeah, you have the other issues, and in that case, if you wish, you can consider time to be a special parameter and work things out in other ways. But
sure. Thank you.
A pleasure. Okay, so moving quickly to numerical experiments. This I don't believe is going to be very long. I'm going to show you some experiments which are on stationary advection diffusion PDEs. The first one is a very simple example, just a way to show you how the idea works out. And here I'm using a convention where e to the I pi mu is the vector cosine of mu, sine of mu, simply a convention to shorten the notation. So it's an advection diffusion where the parameter is the direction of the convective field. And the other facts, the other quantities are fixed. I am on a unit square, and I have a force that is fixed at the middle of the square. Here you can see that the PD depends on one parameter, so P is equal to 1, but the latent dimension of the solution manifold is not 1, it's 2. And this is very intuitive from the fact that I don't have the injectivity with respect to the parameters. If the direction, the angle of the advective field is 0 or 2 pi, I'm going to get the same advective field because I have periodicity of cosine and sine. So I don't have injectivity, and the short answer for why the minimum is 2 is that the solution manifold is homeomorphic to a circle, and the minimal dimension of a circle is 2 because you cannot draw a circle inside a line. Okay, you cannot draw a circle in R, you need at least R2 to draw a circle. And so I'm going to use a high fidelity of 10,000 vertices. These are the results. You can see that the method based on networks is able to approximate the solutions very precisely with an average error up to 1%. And instead, if you use linear methods with this dimension, so dimension little n equal to 2, you're going to get a very high error. And here you also have, as the dimension is small, I can show you what the neural network is actually looking at. And you can see that the solution manifold, the whole collection of solutions, is being represented as some type of circle. And here you have 4 different instances, different points on this curve correspond to different solutions. So here you can see that I'm representing the solution, the whole collection of solutions, as a subset of R2, and in particular as some type of circle that is, in fact, intrinsically one-dimensional. Finally, other 2 very quick results. The second one considers advection diffusion equations with a much more complicated structure because I have 7 parameters. The first 4 ones describe the conductivity field on 4 different circles. So the conductivity field is piecewise constant, but can change parametrically the values inside the circles. And then I have a singular force because the source there is a Dirac delta. and the location of the Dirac delta is parameterized by mu. So it can move inside a square, and this is going to be a mess. And finally, I have the direction of the advective field, which can still change parametrically. And I am fixing two cases with different intensities to see how the difference in the convective field impacts on the performances. These are the solutions where the results, let me say, I'm going to go very quickly. The approximations using the neural networks are the ones in red and green, simply two variants. But you can see that with respect to linear methods, which are the one in blue, you get very, very small errors, and you get a gain in terms of memory because the network is less complicated with respect to the number of degrees of freedom that are needed by the POD, which is one linear method. Let me clarify very quickly that here you can see, for example, in red, I have 4 points because I am considering a network that is heavier and heavier. I am adding more biases and more weights, so bigger network, but the reduced dimension, I am fixing it to be equal to 7 because here we proved that the latent dimension of the manifold is 7. So every time I am compressing 44,000 vertices into 7 numbers every time, but I get an accuracy of 2% approximately. This is on the case of mild advection. When the advection is stronger, you can see that the performance is good on the training set, but becomes worse on the test set. And this shows that for stronger advection fields, the network is still able to overcome the problems of linear methods, but needs more training samples. You have to train it more. These are some results. You can see the form solution and the approximation. They are pretty close one to each other. Even in the case of high errors, you can see that a network is still able to approximate the direction of the flow and the main properties of the solution. Let me conclude with this final example, which is one where I performed the use of these methods to, for example, do the inverse estimate of parameters. Here you have a gas inside a ring, and there are 2 exit holes, P1 and P2. And the question is, I have only 8 measurements down on the outer boundary, so I only know the solution of 8 points. And given those 8 points, I wish to estimate the location of the inner hole. How do I do this? I train a network that is able to know the solution of every possible combination of the parameters, and then I use the network, which is very efficient, to perform Bayesian inversion with standard MCMC algorithms. Here you can see the results. I have the 8 measurements, and this is the final output. The value theta star 2, 0.38, is the angle describing the location of the true inner hole. And here you have the estimate using the network. So you can see that is able to give a pretty good estimate and understand the location of the hole, even though I'm only giving 8 values. And I believe that is enough. Sorry for rushing. Thank you for your attention. Here you have some references, and I'm happy to take questions.
Thank you very much, Nicola. It was a very interesting talk. And yeah, so if anyone has any questions, this is the time.
I popped up my hand there. I wasn't sure if there's a protocol.
Oh, yeah, sorry.
Yeah, so if I could have a question. So very interesting. Yeah. The if you go back to that example with the 4 domains.
This one?
Yeah. So I was wondering if you'd experimented with having the center of those domains as additional degrees of freedom to actually locate those domains as well.
Okay, so to make them move around.
Yeah.
No, I did not. And I believe it would be even worse, because if you allow all of them to move, for example, if you swap
Well, yeah.
omega 1 with omega 4, you get the same situation. So you're going to have even a more complicated solution manifold because you get the same solution with different configurations.
Yeah, so what I was thinking was that if you imagine that if you allow the overlap to be basically topological, so that when you bring them close enough together, you're not counting the area twice of overlap, then in some sense you have an interesting solution landscape to look at there.
Okay, so you say if they overlap, I'm not considering twice, but the union of the. Okay.
So this sort of, in some sense, what I'm suggesting is that if you're thinking of the manifold of solutions as a function of those centers, then you'll have topological events. Whereas
yeah, and I'm pretty sure there you would need a different latent dimension, because in this case, you can see I have chosen equal to 7, which as first one may think that is surprising, because you still have the direction of the transport field, which still gives you this type of circular event, because you still have the angle mu7, but the parameters are 7 and the solution, the latent dimension is still 7. In this case, the short answer is that if you take a cylinder, the cylinder is going to be 2-dimensional. I still have the circle, but the cylinder can still be mapped into R2, because I can represent the cylinder using some type of ring with little width. So
yeah, so again, just the suggestion is that if you thought of your sort of solution manifold in the dimension of embedding, it's kind of a very interesting kind of
yeah, it would be
as you go through such points. And then if I give you the black box, where
it would be, I'm not sure it would be so easy to understand the latent dimension. Probably you just have to take the maximum bound to p+1.
No, I think,
but it would be interesting to understand the topology of it.
Yeah, because I think in some sense that you kind of would extend your concept of manifold, so that you would have basically manifolds which in some configurations of high dimension, but then, so to speak, they condense into lower dimensional structures.
Yeah. Because near the point you have something that,
Okay.
Interesting one.
Very interesting talk.
Thank you.
All right. So, are there any more questions?
I would have a question.
Yeah.
So, hi, thanks for the talk, was super interesting. So I don't know much about neural networks. So I mean, basically nothing actually. So maybe the question is a bit stupid, but so in this case, for instance, where you have 7 parameters and you say that your latent dimension is 7. So if I understood you correctly, you're going from the parameters to some other set of parameters that are like in the number that is your latent dimension, and then you're going from there with another neural network to the solution.
Precisely.
Why do you do this and you cannot just go from the parameters to the solution?
That's a very fair question. That's a very, very fair question, because when I show you this picture, you may say, well, if you are fixing the architectures of phi and psi, why not simply connect phi and psi and train big phi directly as a neural network that gives you parameters to whole solution? Well, the short answer is that the problem with very large networks is that they are very hard to optimize. The optimization problem associated to the finding the good network is problematic. You have to do some gradient descent on the data, but very often you encounter local minima and other type of problems. If you go around the problem and you start by saying, no, let me not train directly big phi, but I start with the autoencoder. The autoencoder is much simpler to train because you are starting with big data and going to something smaller. Instead, you can see that the problem on the other side gives you from very tiny data, the parameters, very high dimensional data, the solution. So it's easier to go around it, and is, if you wish, a way of overcoming the problem of optimization. That's the main point. But you also made a fair point on the fact that, for example, in the case of 7 parameters, the latent dimension is still 7. So you can think of the of the values in the latent dimension as new coordinates for the manifold.
Okay. Thanks. Yeah, very clear. Thanks.
Thank you for your question.
Okay, I think we have yeah, 2 or 3 more minutes, and then we can call it a day. I actually had a curiosity. I don't know if there's anybody who has questions at the moment.
I had one more question. Hands up.
Oh, okay, please. Sorry.
Okay.
I thought it was still the hand of before. So
no, I took it down.
Sorry.
So, thank you. So, yeah, I mean, I'm not that familiar with this machine learning aspect. I've been to a few talks, so I've sort of a sense of some of what's going on. One thing that's on my mind is that you're estimating parameters or fitting, but there's no statistical or stochastic aspects to what you're doing. So could you perhaps speak to what might be the sort of the Bayesian view of this, where you're coming to not an exact choice of parameters, but you're actually identifying distributions which best fit?
Yeah, that's a very interesting approach, in fact, because when I have to optimize the network, every time you have this problem of finding local minima, and instead a Bayesian approach gives you a distribution of the weights and biases, so you understand how uncertain the estimate is. I haven't tried that myself to implement those. I believe, for example, in this case, the problem is that the network is very large. So making this type of inversion for a very high number of parameters is problematic. For example, in this case, in the case with 7 parameters, I have 1 million degrees of freedom.
So in the physics literature, again, in the machine learning literature too, they have something called stochastic gradient descent.
Yeah.
Which I think is a way to get around this this dimensionality curse.
Yeah, it's a way to overcome the problem of local minima in a way, because you try to optimize on, for example, 10 solutions, then you optimize on other 10 solutions. And the idea is that the first 10 solutions can get you closer to the actual minimum. Maybe you are getting stuck to a local minimum, and the other 10 solutions are going to drive you out from the local one. So you keep pushing around and you get to the actual one. But even though you have theoretical results that ensure that stochastic gradient descent almost certainly gives you the best choice, the optimization problem is still very hard. And when you are there in practice, it's very complicated. I believe that that is an issue in the user neural networks, the fact that you don't have an actual control on the optimization. And at the end, the only way to be pretty confident of your model is simply to test it on test data and see if it performs well.
Thanks for the answers. Just a comment, I'm really pleased to see this graduate seminar. Thanks for giving me the space as an undergraduate to jump in. Hopefully I didn't interfere too much with the flow of ideas.
No, of course.
No, I don't believe you didn't.
Thanks.
All right, so I think we're good if there are not questions of the last minute. So thank you again, Nicola, for the very interesting talk. And
thank you too.
I really hope to see you and Clara soon in Milan, because at the moment I'm still here, but okay.
Come back to us.
Yeah. And yeah, and thank you for everyone who participated. So see you at the next talk.
Thank you for organizing. Bye all.
Bye.
Ciao, grazie.
Ciao, ciao.